You know about stars, right? Like our sun, they are these big balls of hot gas. They shine because of something called nuclear fusion. That's when atoms, usually hydrogen, smash together in the middle of a star. They form a new heavier atom like helium. And when they do that, they let out a lot of energy. That energy makes the star glow. It makes the star hot. That's how normal stars work. But then there's this idea of something called a quasi-star. It's a bit different. It sounds like a star. It looks like a star in some ways. It even shines like a star, but it's not powered by the same thing. It doesn't use nuclear fusion in its middle. No, a quasi-star has something much stranger at its heart. It has a black hole. Think about that for a second. A black hole inside a star. It sounds like something from a science fiction movie, but it's a real idea. Scientists think these things might have existed very early on in the universe. They were like the first big bright objects before lots of regular stars formed. They were a step in the universe's story. So, how does this work? How can a black hole power something that shines like a star? Well, let's break it down. First, imagine the early universe. It was a very different place. There were no galaxies yet, no planets, just huge clouds of gas, mostly hydrogen and helium. These clouds were vast, much, much bigger than any gas clouds we see today. They were also very dense in some places. Gravity started pulling these dense parts together. When enough gas collects, gravity just keeps pulling it inward. It gets hotter, it gets denser. For a regular star, this is how it starts. The middle gets hot and dense enough for fusion to begin. And then, boom, you have a star. But with a quasi-star, something else happens first. In these supermassive gas clouds, the core might have gotten so dense and hot that it didn't just start fusion. Instead, it might have collapsed directly into a black hole. This is not how most black holes form today. Most black holes form when a very, very big star dies and explodes, but back then conditions were different. A big chunk of gas might have just folded in on itself, like a giant invisible cosmic paper crumpling up. So, now you have a tiny black hole, but it's not just floating in empty space. It's surrounded by this absolutely enormous cloud of gas. Picture it, a small, super dense black hole right in the middle of a colossal sprawling gas cloud. This cloud is maybe thousands of times bigger than our own sun, maybe even more. It's truly massive. This gas cloud is still collapsing inward because of its own gravity. It wants to fall into the middle, and guess what's in the middle, that new black hole? So, gas starts falling towards the black hole. It gets sucked in by the black hole's incredibly strong gravity. This process of gas falling into a black hole is called accretion. Now, when gas falls into a black hole, it doesn't just vanish cleanly. It gets really, really messy. The gas swirls around the black hole first. Think of water going down a drain. It doesn't just drop straight down, it spins. This spinning gas forms a flat disk around the black hole. We call this an accretion disk. As the gas spins faster and faster in this disk, it rubs against itself. There's a lot of friction, and friction creates heat, a lot of heat, like unimaginable amounts of heat. So hot that it glows with incredible brightness. This is the energy source for the quasi-star. It's not fusion in the gas cloud itself, it's the black hole eating the gas, it's the friction in the accretion disk. That's what makes the quasi-star shine. So, you have a black hole in the center. Now, it's actively feeding on the gas that surrounds it. This feeding creates a huge amount of light and heat. But this light and heat don't just go off into space immediately, they get trapped. They get absorbed by the vast dense gas cloud that is still all around the black hole. Imagine the black hole is a very bright light bulb, and the gas cloud is like a giant thick fog surrounding that light bulb. The light from the bulb doesn't escape easily. It bounces around inside the fog. It gets absorbed by the fog, heating the fog up. The whole fog cloud starts to glow because it's being heated from the inside by the black hole's feeding activity. That's the quasi-star. It's a huge, puffy ball of gas. It looks like a giant star from the outside. But inside, it's not a nuclear furnace. It's a black hole busily munching on gas and shining incredibly brightly from that activity. The gas cloud itself is heated up by this central activity. It becomes a glowing, hot, giant object. These quasi-stars would have been enormous, much, much bigger than our sun, maybe hundreds or thousands of times the radius of our sun. Their mass would have been incredible too. We are talking about millions of times the mass of our sun. That's a truly monstrous object, but the mass wouldn't be concentrated in a tiny core, like in a regular star. It would be spread out in this vast, puffy cloud of gas. The gas in this cloud is so thick and dense that it acts like a blanket. It traps the light and heat coming from the black hole's accretion disk. This trapping is very important. It keeps the gas cloud from collapsing further. The outward pressure from all that trapped heat pushes against the inward pull of gravity. It makes the quasi-star stable for a time. It's a delicate balance. How long do these quasi-stars last? Not forever. They are not like our sun, which will shine for billions of years. Quasi-stars are thought to have much shorter lives. We're talking maybe a few million years. That sounds like a long time to us, but in cosmic terms, it's just a blink of an eye. During these few million years, the black hole in the middle just keeps eating. It keeps growing bigger and bigger. It's like a hungry monster that never stops. As it eats, it gets more massive. And as it gets more massive, its gravity gets even stronger. It pulls in even more gas. This makes it shine even brighter. It's a feedback loop. The gas cloud slowly gets eaten away. It can't last forever. Eventually, the black hole will consume most of the gas in its immediate vicinity. Or, the outward pressure from the black hole's intense radiation might blow away some of the surrounding gas. When the gas starts to run out, the quasi-star changes. What happens then? Well, when the black hole stops having enough gas to eat, its shining starts to dim. The heat source starts to fade. The gas cloud can no longer hold itself up against gravity. It starts to collapse. And what's left behind? A very large black hole. A black hole that has grown significantly during its time as a quasi-star. This is a really important point. Scientists think that these quasi-stars might have been the very first seeds for the supermassive black holes we see today. You know, those giant black holes that sit at the center of most galaxies, like the one in our own Milky Way. They are millions or even billions of times the mass of our sun. How did they get so big so fast? That's a big question in astronomy. Quasi-stars offer a possible answer. They provide a way for black holes to grow incredibly quickly in the early universe. By sitting inside a massive gas cloud and gobbling it up, a black hole could quickly bulk up to a huge size. This could then be the starting point for the even larger supermassive black holes we observe today. It's like a rapid growth spurt for black holes. So these quasi-stars were not just interesting oddities, as they might have been crucial for building the structure of the universe as we know it. They were part of how galaxies got their central monsters. We mentioned that the early universe was different. The gas clouds were purer, mostly hydrogen and helium, no heavy elements yet. These heavy elements are made inside stars later on. This purity might have been important. It made the gas clouds behave in a way that allowed quasi-stars to form. It's harder for such things to form in the modern universe. There's too much stuff around, too many heavier elements, which change how gas cools and collapses. Also, the universe was much denser back then. Everything was closer together. This also made it easier for huge clumps of gas to form. These huge clumps are what you need for a quasi-star. You need a lot of raw material for the black hole to eat and for the gas cloud to swell up. So how do we know they existed? Well, we don't have direct observations. We haven't seen a quasi-star. That's because they existed so long ago. The light from them would have traveled across the entire universe to reach us. It would be incredibly faint and stretched out by the expansion of the universe. It would be very hard to spot. Also, they don't last very long, cosmically speaking. So even if they were around, they would have been gone quickly. We are looking at a universe that is over 13 billion years old. The quasi-stars likely formed within the first few 100 million years. That's a tiny window of time. So, for now, quasi-stars are a theoretical concept. They are an idea, but it's a very strong idea. It's based on what we know about physics, gravity, and the conditions of the early universe. Scientists use computer simulations. They plug in all the numbers and laws of physics. And these simulations show that quasi-stars are a very plausible way for black holes to grow and for early bright objects to exist. They fit in with other things we see. For example, we see very luminous objects called quasars in the early universe. Quasars are powered by actively feeding supermassive black holes. Quasi-stars could be an even earlier, more fundamental stage in the development of these powerful objects. They could be the precursors to quasars. Let's talk a bit more about the star-like aspect. When we say it looks like a star, we mean it's a giant, hot, glowing ball, but its internal structure would be very different from a regular star. A regular star has a super hot, super dense core where fusion happens. That fusion produces energy that pushes outward. This balances the inward pull of gravity. Then you have layers of gas surrounding that core. And a quasi-star, on the other hand, has a black hole at its core. No fusion there. The energy comes from the black hole's appetite. And the surrounding gas cloud isn't just a few layers, it's the bulk of the object. It's diffuse. It's not as dense as the core of a regular star. It's more like a giant, super puffy cloud that's being kept hot and expanded by the energy coming from its middle. The gas itself is mostly hydrogen, and it's very hot, but it's not hot enough, nor dense enough, for nuclear fusion to start throughout the whole cloud. Fusion needs extreme conditions, much hotter and denser than most of the quasi-star's gas would be. Only the very central part near the black hole would be hot enough, but that gas quickly falls into the black hole. The rest of the gas is just heated by the black hole's intense radiation. This outward radiation pressure is crucial. It's a bit like a strong wind blowing from the center. This wind of light and energy pushes the gas outwards. This push keeps the gas from fully collapsing onto the black hole. It keeps the quasi-star from just shrinking into nothing. It inflates the whole structure. It keeps it big and puffy. If this radiation pressure wasn't there, the entire gas cloud would quickly collapse onto the black hole. And then you wouldn't have a quasi-star. You'd just have a rapidly growing black hole without the glowing star-like envelope. The balance between gravity pulling in and radiation pushing out is what makes a quasi-star a quasi-star. Think about the size again. Our sun is about 1.4 million kilometers across. A quasi-star might be hundreds or even thousands of times bigger than that. So, we're talking about something that could easily swallow the orbit of Mercury, Venus, Earth, and maybe even Mars. It's a truly monstrous scale. If one existed in our solar system, it would dominate everything. It would stretch out further than anything we normally think of as a star. The light they gave off would have been incredibly bright. Even though they existed far away and long ago, if you could have seen one up close, it would have been dazzling. They would have been some of the brightest objects in the very early universe. They would have lit up parts of the universe that were otherwise dark. This period is sometimes called the cosmic dark ages, after the first light from the Big Bang faded and before the first stars and galaxies fully formed. Quasi-stars might have been some of the earliest lamps. So, in summary, a quasi-star is not a regular star. It's not powered by nuclear fusion throughout its body. It's a huge, puffy cloud of gas, maybe millions of times the mass of our sun, with a growing black hole at its core. The black hole eats gas, and this eating process generates immense heat and light. This energy gets trapped by the surrounding gas cloud, heating the whole cloud up. The heated gas then glows, making the whole object appear like a super luminous star. These objects would have been around in the very early universe. They were short-lived, only a few million years. But during that time, they served an important purpose. They helped black holes grow very quickly, potentially forming the seeds for the supermassive black holes we see today at the centers of galaxies. We don't see them now because the conditions needed to form them don't exist anymore. The universe is older, less dense, and has more heavy elements. These things make it harder for such massive, pure hydrogen-helium gas clouds to form and collapse in the specific way needed for a quasi-star. So, when you hear quasi-star, think of it as a black hole wearing a very large, bright, and hot gas coat. It's a unique and fascinating idea about how the universe started to build its biggest structures long before our sun or Earth even existed. It's a glimpse into the extreme conditions and strange objects that populated the very early cosmos. It's a theoretical puzzle piece that helps us understand the vast story of the universe. And it all starts with a black hole not burning, but eating.